Valentine. You want to use this, that's great, and there is the Was it too sweet?
I'm very disappointed. If you tell them it's not able to do this, everybody will be silent.
Good afternoon. So I'm Valentin Couvreur, and I would like to introduce you to a new root water uptake model that we recently developed at UCL in Belgium with my co-authors here. So first I will tell you about the principles behind the model, and then some applications about how to empirically parameterize the model. So, the context is that in hydrology, plant root systems impact both drying pattern of the soil and also plant water availability, and these have an impact on crop yield and soil water storage. And these 2 points also are in a very complex interaction. And at the center of this interaction, you find the root system properties. And that's why it's very interesting to characterize these properties. So, well, yesterday Nathalie told me very nice stories about plants going to school and learning physics, and it was really funny. But well, now I will really stick to the official story of water movement through the soil plant system. And so physics tells that actually water moves passively through that system and is driven by water potential difference between the soil and the atmosphere. And because this movement is passive, it's really easy to characterize, well, to describe it with physical equations of water flow through radial resistances here for the entrance of water from the soil to the root, and also actual conductances in the xylem vessels of the plant. And when we take all of these conductances all together in the network of the plant, we obtain what we call the plant hydraulic architecture. And this concept is really at the center of the approach that we developed here. So in 1998, Claude Doussan had the idea to develop a root water uptake model that really takes into account the water dynamics inside the root systems. So from the soil root interfaces to the stem. And for that, he used very complex 3D root architectures. And for each root segment of the root architecture, he had one equation describing the actual flow in the xylem tubes, and one equation describing the radial flow from the soil to the center of the root. And so here you can see the actual conductance of the root segment, and there you can see the radial conductivity of the root segment. So these equations are like Ohm equation in circuits theory. So when you solve the whole set of equations of all the root segments, you can actually obtain the plant collar water potential, which we use to predict stress. Actually, when we reach threshold value, we consider that the plant reduces its transpiration. So this is a behavior that isohydric plants show to have. And we also obtain the root water uptake distribution in the soil. So when we couple this modeling approach with a 3D soil water flow model, like Hydrus or SWIMS, we obtain a very sophisticated soil plant model of water dynamics, like our SWIMS here. But there is a drawback with that kind of model. It requires a lot of information about the root system, and also it takes a lot of time to solve the equations inside the root architecture as compared to FEDE's model, for instance. But recently we actually showed that FEDE's root water uptake model, even when we use it with the compensated uptake, it does not behave like root hydraulic architecture. It cannot behave because the model shape is not suitable to behave like a hydraulic architecture. So after that we made some kind of a crazy bet, which was to actually solve the solve the whole set of equations of Toussaint, which I just showed you before, analytically, which means that we kept all the variables and we just checked out what we would find. And what we found is that the thousands of parameters of each segment of the root architecture, they could be gathered into some kind of macroscopic root parameters. And we have three macroscopic root parameters that appear. So this is the equation that we obtain when we do that kind of macroscopic observation of the behavior of the hydraulic architecture. And so root water uptake, here we have, for instance, a root water uptake in 2D. It equals what we call the standard root water uptake, which is the root water uptake that would happen in conditions of uniform soil water potential. And we have here the compensatory root water uptake, which accounts for the fact that naturally places where the soil water potential is higher, the uptake will be higher. And at places where the soil water potential is lower, the compensatory root water uptake will be negative, which means that the total uptake will be lower than the standard root water uptake. And here you can also find one of the macroscopic parameters, which we call compensation conductance. And actually it accounts for the fact that roots with higher conductances, they can more easily adapt their uptake to the conditions of the soil water potential distribution. And here you can see the second macroscopic parameter, which we call the standard sink fraction distribution. So this parameter is spatially distributed and is very similar to the relative root length density, but it accounts for the root hydraulic properties. So we did the same exercise, but for the collar water potential, which we use for prediction of water stress. And actually we realized that it was equal to the sum of what we call the equivalent soil water potential and the charge loss in the root system due to the transport of water through the root architecture. So this charge loss is proportional to the actual transpiration and inversely proportional to the third parameter, which is the whole conductance of the root system. Obviously, the soil water potential cannot be just a scalar value, because the soil water potential is most of the time heterogeneous. And what we also demonstrated with our approach is that analytically we could consider that the equivalent soil water potential, as we call felt by the plant, is the scalar product of the standard sink fraction by the soil water potential distribution. This means that at places where you have, for instance, more roots or more aquaporins, the plant really feels more the water potential, and so you obtain some kind of weighted mean soil water potential, which is really for this given plant. If you would have another plant with another distribution of the rooting depth, for instance, a lot of roots here, it would feel very different equivalent soil water potential. And this is an analytical solution of what happens in a hydraulic architecture. So now let's talk about the applications. So here we concentrate on the global conductance of the root system. Actually, I don't know if you already heard about pre-down water potential. So this is a measurement of the leaf water potential at the end of the night. And at that time, physiologists considered that the plant water potential is at equilibrium with the soil water potential. And there is actually no transpiration at that time. And what we observe is that at that time, here we have the plant polar water potential. At that time, pre-dawn, the leaf water potential equals the water potential, soil water potential felt by the plants. So, and if we measure pre-dawn water potential and water potential in the leaves at noon, for instance, the difference between them is actually T act, so the actual transpiration, divided by our parameters. So this means that many people actually took these measurements for decades, and they actually had a very, very good information about the plant whole conductance, which is also known as LPR for physiologists. Now let's concentrate on the second microscopic parameter, which is the conductance for the compensation. And here we used light transmission imaging experiments. So actually we have what we call a rhizotron, in which we put sand and a plant can grow in it. And during an experiment of drought of 3 days, we can observe, thanks to pictures that we take with a camera and calibration, we can observe the water content distribution. And when we observe that water content distribution, which evolves with time, we also observe information about K-comp. And this allows us to do inverse modeling so as to characterize the parameter experimentally. So what we also have as information is the root architecture with that kind of experiment. And the problem, if we want the exact behavior of the hydraulic architecture of the root system, we would need the full architecture, which we have, the root ages and types, which we have, but also the root hydraulic properties. And if we don't want to use those that we find in the literature because we don't trust them, and if we don't have the means to measure the root hydraulic properties, then we need to find some kind of proxy of the standard sink fraction distribution. And for instance, here we did a trial considering that the relative root length density distribution is approximately equal to the standard sink fraction distribution. And then we did inverse modeling so as to try to find back the exact value of K-comp. And what we see here, we have the values of our objective function in absolute water content. And what we see is that the minimum is not so far from the real value of K-comp, but well, still this can be improved. So by finding, for instance, a better proxy of the standard sink fraction distribution. So as a conclusion, here I show a summary of the equations that we developed. So for root water uptake, for polar water potential, and for the equivalent soil water potential felt by the plants, and some features of the microscopic model of the root hydraulic architecture. So for instance, is very accurate as compared to the detailed Dusan root water uptake model. It is very simple and as fast as a FEDES root water uptake model in simulations. You can both obtain its parameters numerically by solving Dusan equations, or empirically, as I just showed you. And you can also find a very clear distinction between the stress and the compensatory root water uptake processes, which is not the case with FEDES root water uptake model when we use compensated uptake. So thank you.
Any questions?
With respect to the second point, you say it's as fast as the FEDES model, which is good news, but does it mean that there's a one-dimensional analog for your model? Or is it only possible to
No, so for instance, we don't consider the resistance due to water transport in the soil, which means that currently we use it in Hydrus 3D or in Swims 3D. And we are currently looking for solutions to couple this model with, for instance, the Young-Vanlier root water, the Young-Vanlier model, which would provide the soil water potential at the soil root interface. So this is a solution we're working on, but well, we don't have a very convincing results right now, but which means that we need to solve soil water flow right now, in addition to that.
Go ahead.
Yes. The apparatus you use to take photos for the roots, how thin is the green glasses?
The rhizotron is 4 millimeters.
You developed this experiment, or it is published?
No, I didn't develop it. So here the image is from Guillaume Lebet, who worked a lot with this experimental setup, and it was originally developed by Emmanuel Garrigues, working in France, I think in Avignon. And well, it's quite new. It was developed around 2005.
Thank you.
Yeah.
It doesn't seem like to estimate K compensate. It seems like how to estimate it, no?
Sorry?
Is it easy to estimate K comp?
If you have the right standard sink fraction distribution, then it's very easy because you really get a very steep objective function. But well, here, as you can see, we are more around 1.4, 1.5 the value of K-comp. And here we have a little bit less information during the third day of the experiments, and but it's a little bit better.
But let's say I don't really understand much about the plant.
Yeah.
What do I need to measure in order to estimate it? Like,
so
one thing that I can.
Either you can measure the full root architecture and the root edges and the root hydraulic properties, and then you do some equation and you obtain the parameter. Or you can try to obtain it by inverse modeling, but then you need to measure, you need to see the behavior of the root architecture when there is compensatory root water uptake. If there is no compensatory root water uptake, you don't have information about the conductance for compensation. So here actually what we measured is the water content evolution. And since the soil becomes very dry here and is still very wet there, we have a lot of compensatory root water uptake, and then we have a lot of information over this parameter.
Thank you. Any other questions? What about that side of the room there? Okay, thanks. So now we go to our last one. What is it, Thomas?
Yeah.
Very good.